Alright, so this is going to be the first of at least a couple of videos to talk a little bit about rational functions. Rational expressions were back in our point 5, and that was, I know, everybody's favorite section, but it's something that's going to come back to us now. When we have a rational expression, that means we have a ratio of two algebraic expressions. And when we are going to draw a graph of a rational function, it looks a little bit different than our polynomial functions did. Okay, so here is an example of a picture of a rational function, and I'm not going to tell you what that function actually is right now, but what we are going to focus on, because again we're just going to hit the tip of the iceberg on these, are two things. One of them has to do with the asymptotes of the graph, and an asymptote is a line that the graph approaches in certain situations. So if we notice here, let me get one more, that the vertical blue line right there is a line that the red graph, as we walk at it from the right side, notice that the red line, if we go down and down and down forever, the red line never actually touches the blue line. It'll kind of look like that in the graph, but notice there's always space there if I zoom in close enough. So it gets very close to it, but it doesn't touch it. It doesn't cross it. And sorry to make you dizzy. Same thing from the left. If I walk up this graph from the left, that red part of the graph is going to get very, very close to that blue line. But again, if we keep zooming in, there's always going to be a little bit of space there between those two things. And that blue line, which happens to be, if we zoom in close enough, we see that line is x equals -3, right here, is our vertical asymptote for that graph. Okay. Some rational functions, not all of them, but some of them also have horizontal asymptotes, meaning that as we look at our tails, kind of our end behavior, like we just finished up in 3.4, if we are walking on that graph to the right as far as it goes, if we are walking along that graph to the left as far as it goes, does it approach a certain value? Okay. If we keep following this graph to the right, it comes from below, but notice it's approaching the value y equals 2. If we follow that graph to the left forever, okay, again, still right here, see this little 2? It's going to approach that line. The difference between horizontal and vertical asymptotes is if a function has a vertical asymptote, then your graph will never touch it and never cross it. It's a place where our function is undefined. And we know about domain, and we're going to go there here in a minute. When you have a horizontal asymptote, sometimes the function does actually touch it. Sometimes it crosses and goes to the other side. It's kind of a guideline, and most of the graph sticks with it, but it is possible to touch or cross a horizontal asymptote. So in section 3.5, we're going to focus on how do we find what those asymptotes are, and then how do I sketch a graph using those as guidelines, along with some other pieces of information that we already know. Okay. So if I have a rational function, I'll say y equals p of x over q of x. So some polynomial on top, some polynomial on the bottom. Okay. We know that the domain of this function is going to be any real number, except for the values of x that make us divide by 0. Okay, I'm going to erase the word domain there. No, not. I'm going to put it back. It's all the values of x, so that q of x is not equal to 0. Okay. Our vertical asymptotes, vertical meaning up and down line. If there are going to be any vertical asymptotes of our function, they are going to happen when the bottom is 0. Okay. If there are any vertical asymptotes, they're going to happen when the bottom is 0. Okay. But the top cannot be 0 at that same value. Vertical asymptotes happen whenever the bottom is 0, but the top is not. So if y equals x plus 1 over x minus 1, we know the domain of this function is all real numbers except for 1. And we got that by setting the bottom equal to 0. If we plug 1 into the top, 1 plus 1 is 2. So while 1 makes the bottom 0, it does not make the top equal to 0. So that means the vertical asymptotes, only 1, is the line x equals 1. Okay. Asymptotes are lines. Equations of vertical lines look like x equal a number. Equations of horizontal lines, when we get there, look like y equals a number. There's no y equals mx plus b. Okay. It's just x equals a number or y equals a number. Okay. And I will, from here on out, use a capital V and A for vertical asymptote. If we have y equals x plus 2 over x plus 2, x plus 3. If we set the bottom equal to 0, there are two values of x that we have to stay away from. Okay, our domain for this function would be all real numbers except for -2 and -3. Notice if we plug -2 for x into the top, -2 plus 2 is 0. If we plug -3 into the top, -3 plus 2 is -1. Okay, while neither of these numbers are in the domain, okay, both numbers have to be avoided. If I ask for f of -2 or f of -3, you would say that does not exist. Those numbers aren't in the domain. Okay, but in terms of vertical asymptotes, the only vertical asymptote is the vertical line x equals -3. Okay, x equals -3. Because -2 made the bottom 0, but it also made the top equal to 0. Notice if we look at the graph here, there's our only vertical asymptote. If we look at x equals -2, okay, it looks like there's no problems there. Okay, I say, that's not a big deal. It looks like at -2, we're equal to 1. However, if we come up here and get closer and closer and closer to -2, okay, notice it's undefined. Look how the cursor there made a little open circle. Okay, when you have a point of discontinuity like this, okay, those of you going to calculus, you'll spend some time using the vocabulary. Okay, I don't care if you remember the words today or not, but what that means on the graph is when you're sketching a graph of this function, you have to put an open circle there. Your calculator can't do that. Your computer won't do that. If you draw a picture in Desmos, you can't see that open circle there. And if you scroll up the line, if you trace in on your computer, on your calculator, it's going to tell you when you get to -2, it's undefined. Okay, but at -2, while it's not in the domain, it's not an asymptote. Only x equals -3 is the vertical asymptote there. Vertical asymptotes happen for any value of x where the bottom of your function is equal to 0, but the top of your function is not at that same value. So 1 made the bottom 0, but not the top. -3 made the bottom 0, but not the top. -2 made both the bottom and the top equal to 0. Horizontal asymptotes We are going to work on those and find those by looking at the degrees of the polynomials on the top and on the bottom. Okay, hopefully you've spent some time with that worksheet that had the Desmos links in it. And please, 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 if you haven't, go back and spend time with that. It'll help you hopefully to start making connections with these ideas. But if we have a function, let's stick with p of x over q of x. Okay. If the degree of the top is less than the degree of the bottom, okay, then the line y equals 0 is going to be your horizontal asymptote. Okay, horizontal means left and right. If the degree on the top is equal to the degree on the bottom, okay, then y is equal to the ratio of the leading coefficients. That says leading coefficients. Will be your horizontal asymptote. Okay, I'll go back to the last page and show you that here in a minute. If the degree on the top is bigger than the degree on the bottom, there are no horizontal asymptotes. Okay. If that degree is just bigger by 1, x to the 4th on top, x cubed on the bottom, x to the 10th over x to the 9th, x squared over x to the 1st, x to the 1st over a constant, then that asymptote, there would still be an asymptote, but it's going to be what we call oblique asymptote, and it will be a straight line. We didn't do long division back in chapter R. We're not going to talk about it now. If you need to find those later on in a later math class, then you'll be able to do that. Okay. So if I look at y equals x plus 1 over x minus 1, the degrees are the same. I have x to the 1st, top and bottom. That means if I look at the numbers out in front, the leading coefficients, I would say y equals 1 is my horizontal asymptote. Down here, I have x plus 2 on top. If I FOIL on the bottom, I have x squared plus 5x plus 6. The degree on the bottom is bigger than the degree on top, so that means the line y equals 0 is the horizontal asymptote. If the degree on top is bigger than the degree on the bottom, then we say there's no horizontal asymptotes. Okay. There'll be another video that has some examples on it because this one got a little bit long. We'll talk about graphing rational functions.